Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, good morning, everyone. It's my pleasure to welcome Chris Stewart, who's an assistant professor at The Ohio State University, who's visiting us for the day as part of a larger West Coast tour, we understand. Chris's interests are in networked and distributed systems, particularly two sort of areas, one in sustainability and one in performance. And based on the title of this talk, I assume we're going to be hearing more about the latter. So take it away.
All right. Excellent. So if I were Troy McClure, I would start this talk with, you may remember me from such research as. For those, many are good friends, so it's happy to see you guys again. And for those that are just meeting me, I graduated from the University of Rochester late 2008. My work there was mostly on modeling and system management for internet services. So there, the idea, we started with some early work published in NSDI 05, my second year of grad school, and we had some works going all the way up through 2008. And the basic idea there was to come up with some first principle models that gave us good ideas about what response time would look like as we changed the number of nodes in a system. So we could do things like capacity planning, anomaly detection came a little bit later. One of the great things about doing a set of slides like this is you get time to sort of think about, looking back at the high-level contributions that these things had, right? So here I think, with this particular work especially, the contribution was on the simplicity of the model. So we started looking at queuing theory, which at the time people weren't really looking too deeply into for internet services. I think there was a paper from Duke, and Amin Vedat's group was working on some similar stuff. And we showed how to use system metrics that you can routinely collect at some middle layer. Like we instrumented the OS, but today it's done in a lot of middleware systems. We showed how to collect these metrics and how to apply them in a fashion that system managers could actually understand and implement, right? So when I was at HP for basically the latter part of my PhD thesis, I spent working with folks there. We ended up shipping this out to a product group, and this paper, I'm told, has influenced some other people at other companies that ended up being able to apply these in practice. So around the time this was winding down, conveniently it was around the time I was graduating. So I figured it was time to switch areas, right? And I did a one-year postdoc with my advisor. So I started looking at performance anomaly detection. And here the idea is to use these models that we were developing before and use them now as the base system, right? Instead of trying to use models to predict what the real system is like, we want to say, hey, the real system should look like these models. And here, there was a really nice interplay between some machine learning techniques, especially here. So we looked at trying to characterize whole space for this anomaly depiction stuff. Most recently, or second most recently, I left the systems community altogether and started looking at data center architectures. In particular, in 2009, early 2009, I was caught up post-election cycle. I was all about renewable energy at the time. So I was looking at how can we power data centers directly with solar panels. And we published one of the first papers on that at Hot Power, and it's been pretty well received. So now there's an emerging community in the sustainable computing area, and I'm the editor of the Sustainable Computing Register, which is an IEEE publication from the IEEE STC on sustainable computing. I'll say that again, the IEEE STC on sustainable computing. I encourage everyone to join. It's actually free. This is a new model for IEEE where we're just trying to bring together experts, researchers in the field with a common interest area. So after this, I decided, okay, let's get back to the heart of what I work on. And how can we do things that are very relevant to business, to industry, in terms of performance and system management, without losing the sustainability focus. And this is what my talk will be about today. And so I'm going to give you guys some discussion about actually some things that are very recent. So these are papers that are in the pipeline, stuff that hasn't been published yet. So I appreciate your feedback, and you can ask questions at any time. I think I've slated this talk for about, I think I have about an hour, but the talk is about 40 minutes without interruption. So feel free to ask questions at any time, and I can manage. If I can't answer, I'll just pretend like I'm running out of time, and we'll go from there. So at a high level, my current research goal is it comes from the intersection of three trends, right? So from the hardware side, SSD is faster than disk, PCM is faster than disk, and the total capacity of on-chip caches is still growing, right? So we can still fit more transistors on chip, at least for a few more years. So we have the ability to access more data quickly than we ever did before. On the software side, that has been a timely occurrence because there's been, this huge data explosion, right? So we want to perform analytics on top of any and everything. By we, I should say, there are certain companies that want to perform analytics on top of any and everything for whom analytics is their profit margin, right? So being able to predict what people are doing is very important. And here, intuitively at a high level, the closer to real time you can get with data analytics, presumably the better your profit margins can become, right? It doesn't hurt you to be able to do things faster, right? And then finally, the human aspect, the human interaction aspect, some would say this is surprising, still isn't getting much better, right? So the time that you have to do all of this data analytics is still about the same. So if this is a really neat website called humanbenchmark.com. They just show you a red box, and they ask you to click as soon as this red box turns green, right? So just measuring your response time. This is the range of the scores, 215 to about 500 milliseconds. Still same place it was in the early 2000s when we first started looking at interactive.
How much of that is a motor nerve from the brain to the fingers?
I don't know. So I think that
if you ever stub your toe, you notice there's a noticeable time it takes.
Yeah, I don't know why we're so slow. In particular, I don't know why I myself am slower than others. Actually, when I did this benchmark, I was upward of 500 milliseconds plus. So there is a biological answer here. And at a high level, you could say maybe we could find ways to reinvent computers to circumvent some of these biological constraints, right? Maybe allowing response time to be a function of how fast we can blink rather than click. Maybe that's a little tangential to the main point here, but it's an interesting thought. So with the way I view these all sort of combining together is that we're going to want to be able to run data analytics of moderate scale on moderate amounts of data very quickly in as close to real time as possible. So we're looking at emerging applications that are defined not by the interaction time between a service to a human, but between a machine to a machine, right? And we need to do a lot of those interactions before we go back out to the human, right? So at a high level, we're trying to get at emerging applications that have a demand for very low latency, but also very strict SLAs. And I guess I'll define that on the next slide. So the general outline here is, first I'm going to talk about the types of applications that I've been targeting in my research group. Then we'll talk very specifically about our key value store that supports these types of applications. Show some results and conclude. So when I say very strict SLA with low latency, by low latency we're talking about the bound in a service level agreement. So the K% of requests must complete within X amount of time, where X amount of time is defined in terms of milliseconds. And K% of requests is defined in terms of number of nines, right? So this long-held goal of trying to get to multiple nines, like the telephone industry, for access times. So here on the bottom, I'm showing the difference between what I see as emerging services and traditional services. Your traditional service had a couple of different layers, but in the end, when it got to the data store layer, you only had a few machines issuing accesses before you responded back. For instance, you did one lookup in a user query table to see what their most recent purchases were, or to retrieve their cookies or something like that. With these emerging services, what we're looking at is middleware that sort of encapsulates a lot of what is previously done at the database layer. So transaction processing. Also performs some complicated data analytics business logic, right? And is issuing a lot of requests to your backend data store. So here the thickness of the lines indicates the number of accesses issued by these components. So why do they issue more accesses than previously? Two reasons. One, you're doing more complicated tasks, like data analytics of some sort. And these backends have gotten simpler, right? So where a database gave you the ability, for instance, to do transactions, your key value stores may just give you the ability to do gets and puts. And
so just to be clear, so when you say data analytics, I mean, so I'm trying to figure out what your scoping target is, right? Because there's one kind of data analytics, which is like crawling over trillions of web pages and stuff like that. And there's another type of data analytics. Think about Facebook, things like that. So somebody's profile page loads, you're trying to figure out which post should be shown and stuff like that. So there's much different scale requirements and things like that you need for both of those.
right,
And so can you give some example applications like what?
right. So as a high level, you can follow those will highlight, and those are all example applications that I'm going to talk about on the next slide, James. It's coming. But to answer your question directly, it would be closer toward this Facebook side, right? So a moderate amount of data that needs to be analyzed and searched very quickly.
As a phone company, after all, builds itself as a lifeline service, so 99.9% reliability makes sense. If you try to make money, wouldn't 90% do it? You make money on 9 customers and you lose the sale of the 10th, and if you're ahead of the game on other ways, don't make sense.
So the reason here is the user isn't involved on all of the requests here, right? So you're right. If 1 out of 10 users has a bad experience, maybe we're willing to deal with it. The problem here is most of your accesses are happening at this layer. That is machine-to-machine interactions. So a few slow accesses every 1,000 requests means that everybody is going to see a very slow service, right? That's what we're getting at.
At the user level, you lose 90% and then it's bad.
Exactly. So take a look at some concrete applications, right? So one domain that we've been targeting is the scientific cloud. So the goal here is not to replace the supercomputer. That works very well for the types of applications that it targets. But there are many scientific applications that don't utilize supercomputers well, right? So these, if you run them, they run on a small portion of the supercomputer. They don't need to run for months at a time. Maybe they're running for weeks now or several days. And what we would like to do is make those simulations move from an order of magnitude of days to hours or hours to minutes, right? And what I'm showing you here is a concrete example. So we're looking at a smart grid simulator that we've instrumented in my lab. One of the collaborators that I've been working with, actually out here, Bonneville Power, I think they're based in Oregon. I don't know if they reach all the way out here or not. Maybe not. So one question you might ask is, okay, there's been an increase in demand. So should I increase the amount of hydropower that I'm producing, or should I ship electricity in from elsewhere, right? And if you have a smart grid, you have also devices that may adjust their behavior if you tell them to. Well, how does all of this play out, right? You really want to have an idea of this, so you'd like to be able to run simulations to get an idea of what's going to happen before you do it. So the way this particular grid simulator works is you have a master node that's going to set up a lot of, for instance, global variables and just do some maintenance work. And then it's going to start all of these different simulation agents. For instance, if you're modeling houses that all have smart air conditioners that are going to react to messages from the power company to indicate when electricity is quite costly and then turn up the heat, right? You want to have those modeled. You want to have the free market price changes modeled. For instance, if you start producing more hydro, that's going to affect prices. And you need to model people's personal behaviors. All of these simulated agents have input and output files that they need to access in order to do a correct simulation, as well as global variables that need to be accessed consistently over time and shared across these different agents. So, one more? Excellent. So one of these simulations, one of these relatively short simulations, so just simulating the effects across 3 days, you can issue over 10,000 storage accesses. And right now, if you just put this on one node and ran it, you're talking about a little over an hour, a little over 2 hours to do a single computation, right? Which is too slow, because your power operator really would like to be able to do these simulations on the order of minutes to get an idea of demand response.
So are these jobs I/O bound? Are they CPU bound? Are they some combination?
They're a mix, right? So at some points, they go through different phases. So at some points, they may be I/O bound. At some points, they may be CPU bound, because, for instance, maybe an agent is trying to update or model a person or something like that. So once again, going back to the earlier question, so if you have 10,000 requests in here, if you're only meeting an SLA of 95%, that means you're going to have a lot of slow accesses, right? 5% of 10K is a relatively large number. So you really need to have a very high SLA in order to guarantee that you'll have low latency on all of the accesses issued by this smart grid simulator.
Can you give us a little intuition for why? I'm not sure I see how that follows, because it seems like if you model one of these agents, just trivially is, it just has to get through 10,000 accesses. It seems like what would drive the total simulation time is the average access time, not the worst case average time. Right.
So the intuition here is that this is a time step type simulation. So in order to simulate the next minute, you need the results from the prior minute. So if you have a couple of slow accesses, what they're going to do is slow down. They'll prevent you from moving forward, right? Whereas if you, for instance, if this were more like a web server, right, where just everybody throws all their requests against and you get what comes back, then you care about the average, right? But here you can be, and we'll show some data on why on exactly how that has an effect a little later.
So this is like the straggler problem with MapReduce, right? You got a barrier.
Exactly.
One straggler holds the barrier up for everybody.
Exactly. So looking at some of the data analytics features.
Sorry. I guess intuitively it seems like, can't they just have a rule of thumb and some analytic formula that they plug in, how many smart air conditioners they have, and the average power, and the cost of various things? Couldn't you get a really good approximation that you could run in a second? Why do you need to do this elaborate simulation? Why do they want to do that? Why is it such a chaotic system where a small change and I mean I can't imagine that it.
Well, the smart grid, if its ultimate glory were ever realized, the smart grid would be an incredibly complex distributed system. You can imagine if everyone had their own meter that's fluctuating and changing over time, and people have the ability to, for instance, turn that meter on and off, right? It can be, now, I think your question is very valid. What is the actual impact of those things, right? Is it that it just sort of converges to some global average and, you don't, that I don't know, but presumably we would like to be able to run the tests to see if that, if that happens. This is just something that has been of interest to the folks that are building the smart grid, but you see how that would work out in practice. So from the data analytics perspective, I guess what we're looking at, the example I'm providing here, right, is in terms of email, right? So what if you wanted to do some sort of targeted ad placement, right? And actually some previous work here from Microsoft sort of motivated this. So they were looking at searches at Bing, and they found that if you could look at the recent log of searches that had been performed, you could improve the recall accuracy by something like 25 to 50%. This was an interesting study. More generally, I think social networks and whatnot provide even deeper data here, right? So can you detect when when there's some sort of crowd phenomena happening, or when there's a trend that is changing the meaning or context of words for better targeting of ads, right? So here the challenge is the data is changing frequently, so you could use some old data, which is what people pretty much do nowadays, but more up-to-date is better. And it would be even better if you could do some sort of dynamic feature extraction from the query. And to give a very concrete example, we sort of view this as being very akin to deep Q&A, like the IBM Watson project, right? What happens here is you give input of some text, right, that, for instance, in Watson may have been a question, a sentence. He said this, and then you want to extract from that text not just keywords, but some context also. And the way this is done actually was very interesting to me as we looked into the NLP approaches to this. I call it a big set of if statements. So we have an idea of what context looks like here, 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 here. We need to check against all of these. And based on that, you issue a lot of storage accesses and try to retrieve relevant content. So this idea sort of follows into a MapReduce model, but the key idea is you're time bound, right? So Watson, they were trying to do 2 to 3 seconds to win at Jeopardy. By the way, this quote, does anybody know this one? Simplicity is a great virtue, but it takes hard work to achieve. And education to appreciate it. This is Ed Dijkstra, one of my favorites. So, ideally, you guys will believe that my ideas are relatively simple, but also impactful. That's where we're trying to go with this. Once again, this is a real system that we have up and running, right? So we have GridLab D up and running in my lab. We have OpenEphira, which is actually what the earliest versions of Watson was built on. running on our system with data sets. One fun data set is from Usenix. So we've crawled all of the Usenix web pages, and we can tell you about your history of service to that community in particular, what PCs and whatnot. And then finally, because I do still care a lot about the sustainability side.
So we were talking about stragglers before. So to a first approximation, what fraction of the problems that you're trying to solve are quote unquote just straggler problems? I mean, is it?
We care a lot about stragglers, actually.
Would you say like that's the main thing that's keeping people from satisfying these SLAs? The fact that if there were no stragglers, then satisfying SLAs would actually be fairly straightforward. But the fact is, there are stragglers that straggle in different ways.
Well, there's still some issues with just queuing and managing workload fluctuations. But this talk actually is specifically about the stragglers. So that's when we get into some of the more technical aspects. That's what we will be talking about. So, so the idea here is you have these. With the ability to beat human perception now pretty easily, right? Computers are fast enough that we can respond pretty quickly. One way to think about that is it can give you some leeway with the SLA, some opportunities to invest in other things when you would have originally invested in, for instance, more nodes. So our idea here is we want to meet an SLA using as few resources as possible, and then exploit other competitive advantages. For instance, going carbon neutral, Microsoft, right? And how can we turn those into profit? So another application that we've set up in my lab, you'll notice the URL is just sort of like a random IP address. Green mail or mantis mail, or I don't know. We have to come up with some internal name for it. This is a carbon neutral email IMAP cache. And what we would like to do is be able to provide differentiated SLAs to different users based on their desired level of greenness. That is the amount of carbon offsets that they would like to receive as they access the site and the frequency with which they access the site. Here, once again, we want to use as few nodes to meet the SLA as possible so that we can have as many so that we can buy, within a budget, as many carbon offsets as possible for our sets of users. So this is another one that we have set up. All of this comes together for the technical focus of this talk, which is Zoolander. This is our key value store on the back end. So without further delay, the basic idea behind Zoolander is this. For years, we've been looking at using replication and partitioning as our ways to manage SLAs, right? And so here I'm depicting an awful JPEG figure. The basic concepts here, right? So partitioning means you have some set of keys or groups of keys, often called shards, so you put keys together. And any writes that are going to one shard go to one node, writes going to this other shard go to another node, right? Replication, traditional replication, or what we call replication for throughput, says, hey, I want to evenly divide the accesses, so I'm just going to, whenever I get a write, I'll send it to one node, next write, I'll send to another node, so forth and so forth. Now, the basic idea behind both of these approaches is that you want to reduce queuing. You want to reduce the amount of work that each node has to do. And it's worked very well. It clearly can get us up to this 95 percentile SLAs. The challenges here traditionally have been in terms of managing hotspots and consistency. So if you do partitioning, if you have more accesses to one key than another, you have a hotspot, which means you've added a node, but you haven't divided the workload in half. If you do replication for throughput, sure, you divide the accesses evenly, but in order to maintain a consistent view of data, the nodes have to interact with each other. You still haven't really divided the workload in half, right? Now that's the traditional problem. But as James was pointing out, we're actually concerned about a different problem. We're actually concerned about stragglers. And so the key problem here is even if you have perfect division, even distribution of workload, and very light arrival rates, your ability to reach these very strict SLAs that we need to ensure that something like 10,000 accesses all happen very quickly is actually still limited. So here you're looking at an experiment that we did on Zookeeper, where we had just a very small key range that we accessed with no concurrency. And on the x-axis, you're looking at the latency of each access, and the y-axis is the cumulative distribution function. Right? So your SLA that says something like 98% of accesses is just a question of reading horizontally along here to the intersection of the line on the x-axis, and that tells you your latency bound at that point. This figure should be a little bit depressing because what we're saying is you can see all of these very heavy tails here. And what it means, 98%, 96%, 91% for read-only accesses, writes, and writes to a actually dependable store can actually be processed within, that bar is 3 times the mean. So that means most of the time, that means with a I shouldn't say with a high probability, but getting to 99% that is relatively close to the mean isn't possible under just this experiment.
This is a function of the arrival rate, right? So if you use more machines, you partition to more machines.
No arrival rate here. This is just take an access, issue it, wait for it to come back, issue another access, wait for it to come back. This is no concurrency. And like I said, it's sort of depressing, right? So you can't divide this.
So what is the cause for it not to be equal every time?
Okay, so I'll get there. So I just want to point out before that this actually happens also across other key value stores, right? So we've looked at Cassandra, Zookeeper, Memcache. These are all popular key value stores that people are using. So what are some of the reasons for this? You have background jobs, right? So for instance, Cassandra has this write buffer issue that you issue a write, it tries to respond as quickly as possible by keeping a buffer of your writes. This is great, high throughput, right? I can batch all of these buffer writes together. The problem is, every so often, a request can get stuck behind one of these buffer writes, right? So if a buffer write occurs once every second, and it's taking you, a typical access is taking you just 1 millisecond, right? Then you have this good chance that, or not good chance, that you have 5% of your accesses are going to be affected by possibly this write buffer flush. Now, if you only have, if the write buffer flush stalls the request, if it requires stalling the entire system, maybe a write buffer flush, you may say, doesn't have to do that, but definitely garbage collection or DNS timeouts could, then you're going to talk about having almost a 10x increase for that particular request, right? For these background jobs. So
it seems like then there is an arrival rate. In other words, if there's a background job and there's some arrival rate, it's not that you're issuing requests in isolation. You're issuing requests, and other people are also issuing requests concurrently. Is that what's happening?
You could call it. You can call it queuing. You can call it queuing, but these aren't particularly requests that are coming from nodes in your system for storage access, right? This is a part of the system itself. Cassandra just keeps this write buffer access.
What kind of background jobs do you mean? Are you talking about background jobs, other things accessing the key value store, or background jobs, other?
So just to maybe explain this example a little better. So Cassandra keeps a write buffer. Eventually, you have to flush this write buffer just to keep your data dependable, to get it on a place that is reliable. That is a background job. The process of flushing the write buffer is a background job. Garbage collection would be what we're calling a background job here, or updating, or
Antivirus.
Mhm.
Antivirus is the biggest, is the biggest virus of all.
So if we look at this, this is an interesting issue. So what we found is that these things that are causing the heavy tail tend not to be correlated with a specific access. So it's not a function of the input that I'm giving to the key value store. It's just something that has to happen over time. And as we saw, if I go back, these are some pretty big delays, right? So every now and then you get these, you just really get whammed with slow delays. And this has a big impact, right? So earlier somebody was asking me about the barriers and the impact of stragglers, right? So if we look at that GridLab D workload again, and now we're going to actually inject stragglers into the system, right? So on 2% of our accesses, we're going to inject a delay, right? And we're going to compare that to injecting the same delay, the same total amount of delay across all all accesses. And the idea, the takeaway from this is, so this dotted line represents linear slowdown, right? So if we inject across all accesses, we can actually do better than the linear slowdown. Why? Because we can mask things with computation, right? Because you have to compute, so you can compute while you're doing I/O in the background, and it's a slow delay. It's not a long delay, so this is okay. But if you focus these delays on just a couple of stragglers, you start to run into trouble, because now the delay is long enough that you're delaying these barriers as you go through, right?
You're saying that delaying all requests by 20% has less an effect than delaying 2% of the requests by 20%?
20%, it's the same aggregate amount of delay that you're injecting.
Oh, so you're taking the same total delay budget and concentrating it into a small number of things.
Exactly, exactly. So here, on this line, you may be adding, say, for instance, just 200 microseconds to each request, rather than divide by 52 milliseconds to each request.
This is the average delay you're adding.
Per access.
And the series is the standard deviation, if you will, of the delay that you're adding. In other words, at 20%,
The skew.
the skew, the skew
Exactly.
distribution.
Exactly,
Okay.
exactly.
So which line is the linear slowdown?
The dotted line.
The one that labels all requests.
Yeah, sorry, so this is reverse. That is reverse. Whoops. Yeah. Okay. So here's the key insight behind Zoolander. I really like this work. So key insight is we want to revisit this very old technique called replication for predictability, which I think falls in line with this old paper by Jeff Mogul called An Old Dumb Idea Whose Time Has Come, right? And the basic idea behind replication for predictability is you make n copies of your data, but instead of sending each request to one of n, you send all requests to all n, and you take the fastest response back, right? Now, so it's a dumb idea. Why is it a dumb idea just off bat? You don't improve throughput this way, right? So you're issuing the same amount of work to all of your nodes. Why are you doing this? It turns out to be a useful idea now because it reduces the variance, right? So that heavy tail, you're less likely to get stuck behind the heavy tail if you do something like this. And here we're showing this, right? So
It's not clear that it's a win, right? Because you're reducing the capacity of the system by a third. So you're comparing now the 20% of the 2% curve to in other words, the whole capacity is going down. Your hypothesis is that those curves cross in some place.
Yep. We'll get to that. We'll get to how we can answer that. So here we're just showing a high-level depiction of what's happening here, right? So here along this strip and along this strip, we have requests that are arriving. And here we're showing one of these anomalies happening. That is replica 2, or when we do replication for predictability, just to use different terms, we call it a duplicate, right? So replica versus duplicate, partition versus duplicate. So the key point here is the second request on traditional approaches would get stuck behind this write buffer flush and wouldn't finish until here. And if you have a write barrier, if you have a barrier, meaning this third get can't happen until this responds and it does some computation, well, you've delayed the entire execution as a function of the write buffer, right? That's what we just saw in the previous graph.
So I'm probably getting ahead of you, but you probably are going to say this is on slide 22. But what about sources of that will happen? If you're doing the same thing on everybody, then maybe you'll trigger the write buffer flushes at the same time on everybody. And
right.
Garbage collection takes place at 3:00 p.m. and how do you make them get skewed?
Yeah. We'll get to we'll get to some of the things that we do to deal with that. So the key idea here is if you instead just using 2 nodes, Jeremy, right? Did replication for predictability here, you would actually get this response back sooner, and then you'd be able to start the third request earlier, and you'd get a speed up here, right? So this is the situation in which it helps.
So what does this do to power consumption?
Well, if you use the same number of nodes, it keeps power consumption the same. So here you're looking at just 2 copies of 2 nodes running the same copy of data. Presumably, maybe you could argue if you're energy efficient and you're, most nodes today though, you have 2 nodes running, it's 2x the power.
Okay, so just to be clear though, so that means that your claim is that power is essentially just a straight linear function of how many nodes you have in the system.
Rather than the amount of data hosted on each node.
Or the number of requests it's processing.
Yeah,
I think that's what
right.
she's getting at.
That's right. Yes. So
Yeah.
in other words,
Yeah.
it seems like right now what you're doing is actually giving more work to the nodes, even though.
Yeah, that's fair. That's fair. You're right in that sense. So we haven't considered energy yet. If you are energy proportional as a function of the request accesses, or actually as a function of the amount of data stored on the node, this approach, I could see some issues.
Request though, right? So that's the key thing.
Yeah.
So I can't buy the claim that it's just faster in an absolute sense sending to both, because in a system that has a lot of competing requests, one of them, or all of them, are getting delayed by the fact that, for example, duplicate 2, which had an ignored response, could have been processing somebody else's response instead, and so it would have finished faster. I mean, you can make an argument that this particular request you're drawing finished faster than it otherwise would have, but that was at the expense of some other request that would have finished sooner and is now finishing much later because it got pushed back in the queue.
So there is, right now I think we're trying to motivate the high-level intuition, but we do not contend that this should replace all of the prior work that we've done on partitioning and replication for throughput and these other techniques, right? But maybe in some cases this is something that we may want to insert and use when it is appropriate for certain appropriate workloads. So the answer is, if you agree with me that this is a situation where it can benefit, then I should only have to convince you that I can figure out when this situation occurs, and that there's situation occurs in non-trivial cases that are not made up, right?
Well, I think you convinced me that the first request that comes in is faster, but it seems like all the subsequent requests would be slower.
So in a system where you're contending for example, seeks on a disk, for example, like in a system where you have multiple requests outstanding at a given time, I mean, it seems like this is going to increase queuing delays, right? Because in this system, you're actually sending more requests to each disk head, right? And so it's having to move around, possibly wasting work, it seems like, because, in this example, the replication for predictability, so duplicate.
not to get too far ahead, but yes, if you have shared resources on the back end of this, if you have a shared disk, for instance, on the back end of this, that would create problems. And that would definitely be something that we want to avoid. Yeah. So there is a need to avoid having, I'm sorry, I put my hand at the wrong place. So if these two duplicates had shared state here, right, you have to account for these dependencies. And this is something that we've tried to account for.
It's not even just shared state, right? If you look at the workload that duplicate 2 is doing compared to, duplicate 1 versus replica 1, replica 1 only had to process 2 requests. Duplicate 1 had to process 3 requests. Right? There's more work that the duplicate 1 had to do than replica 1. So if you had a situation where there was queuing, which I think this is where James is going, then you're going to increase the queuing delay in the second case. Even though the individual request may finish sooner, you've increased the queuing because you've increased the load.
I agree.
I'm looking forward to seeing your evaluation where you say, look, it really does work.
Yeah, no. I totally agree with you guys. In fact, I think your intuition is exactly right. So a key plot that I will show hopefully in the next 10 minutes will be a function of utilization over time and how this approach compares with partitioning and replication for throughput. So we are getting there. We are getting there.
Well, my intuition is that if you showed us where the tail is 10 to 100 times, if it's more than 2 times, then you can afford to have the number of machines so that you have available, so that you can. Okay, maybe you double the queuing delay. It'll move the mean over by a factor of 2, but you're still better off because the tail.
And your intuition is exactly right as well. So
queuing's nonlinear also. Right.
Yeah, that's a problem.
Yeah.
So go ahead.
What about data consistency? So if you're reading and returning the first reply, but you really want to read from the quorum now, but you're not. So what?
Yeah, we'll get to this. Actually, I won't focus on this too much in the talk. At a high level, what I can what I can say to you now is, so you saw this GridLab D is hosting shared variables, right? So it requires consistent access. So what I'm going to tell you at a high level right now, and sort of skip over a little bit in this talk just because short on time, is our key value store supports that. So we can do strong consistency, we can do read my own write consistency, or we can do write order consistency. And I'll describe some of the mechanisms for that support, but we could talk about it offline to talk more about exactly how to do that.
We'll have time for a little Q&A at the end too.
Yeah. So now we're not the first people to do this. Actually, Microsoft, either in its hires or in its own papers, has been doing this before us, right? So Manstry at OSDI, these guys were looking at doing this MapReduce task scheduling, and they were running things twice and running 2 copies of the same task, taking the one that responded fastest under certain nested conditions.
The first Google paper did that. The original MapReduce paper does replication. They just do it in a smarter way, like whom to replicate. But the general idea of to send 2 replicas for MapReduce and take the fastest, that's in the original first paper by Google.
Okay, I believe you. So, and then Peter's work, SCADs at FAST, is actually, I think, the most related. So they were looking at specifically high SLA key value store, and they were issuing their reads to 2 copies and waiting for the fastest one to respond, right? So the difference between our work is we're providing full support for this approach. So we actually think this approach is really neat. Rather than just trying this out on a couple of duplicates sort of conservatively, saying, hey, we've got 2 copies and we only want to do it for reads, we want to support reads and writes at scale. This is our goal. I'll show you some tests on up to a 32 node cluster for a single partition. So in order to provide that full support, we have to do a couple of things. So we have to manage these read and write accesses for consistency, support scaling out. And importantly for this talk, what I'll focus on is the modeling, right? Because this is the part that I really love. And of course, there's also adapting to workload changes, failure recovery, some of these other traditional aspects to managing a data store, which we deal with also, but I won't focus on too much here. So I want to give you a high-level idea of the type of support that we have to have and how we go about addressing that, right? So if we add this into the mix, our whole point here is we want to add this into the mix. So we want to be able to scale the number of replicas, but we don't want to say that this is all we want to do, right? We want to also do partitioning when it's appropriate. We want to do the others. The problem is we've just had a SLA violation. How do we decide which of these approaches is the appropriate approach to take to resolve this SLA violation? And so for that, what we're going to do is come up with a performance model that is a little bit different from past models. Rather than predicting something like average latency, right? What we want to predict here is the service level, where the service level, if you recall from some previous slides, is that percentage of requests that will complete within a latency bound. So this is an important point here. We're predicting percentages here, not latency, right?
Clarity there. When you say that there's been an SLA violation, there isn't actually been an SLA violation yet, right? That you're expecting, like you said, 4% of requests had taken longer than 15 milliseconds, where you're allowed up to 5%, right? Wasn't that the case? Or you
no.
Saying there really has been one?
Yeah, we're trying to hit SLAs that are multiple nines, right?
Okay,
so no less than 99% is, yeah, this is what we want to
You're
head
not
to.
trying to predict the fact that, oh, we want to take some action now so we don't really miss it.
Yeah.
We really have missed it already.
Yeah. You've really missed it. So here's sort of the bird's eye view of our model, right? So we're taking as input some system metrics like arrival rate, service time distributions, and network latency, as well as target SLA, right, in terms of service level and latency bound. And I'm going to show you a whole bunch of equations inside of here that really are just a function of some first principles about the way replication for predictability should work, based on the example that I've shown you. At a high level, just the model by itself is going to output the expected service level, right? So we're going to get a percentage out. You give us a latency bound, we tell you what kind of an SLA you could actually support at that latency bound. The way you really want to use this is you want to iterate over this, right? So you want to take as an output that service level, compare it to your target, see, well, maybe I'm not meeting the target yet, so I should change my node layout some kind of way, and iterate over here. So there's a replication policy as well. And that replication policy is going to tell us, should I use partitioning? How much partitioning should I use? How much replication for predictability? And our the jargon that we'll use to do that is, say, for instance, we'll have 4 one-duplicate partitions. So here, each shard is on an individual node, right? So this is just traditional partitioning. And two duplicate partitions means we have 2 nodes, each serving these shards, right? So I'll sort of fall back to this in explaining a little later, but this is the jargon.
When you say service time distributions, it's one of the inputs. You're talking about the observed CDF of.
Yeah. Yep. From.
And then you're assuming they're independent, identically distributed for multiple replicas. That's, I guess, Jay's question, really.
Yeah. They can be. Yes. They can and they cannot be. Our model considers both, but we focus on the case where they're the same.
Anybody try to duplicate the shards by array methods like m out of n? So you ask for 3 copies and any 2 come, you can.
Yes. So there's this relationship to quorums, right? Quorums are great if you want to do this on top of reads, but when you start dealing with consistency and writes, you need some more support. So the key idea here is this. So there would actually be 2 problems if we did this fully, right? So if we gave you a model that accurately predicted what happened when you added partitions or when you did replication for throughput and you had this consistency, That's a problem in its own right, right? And people have been struggling with how to model and understand the effects of hotspots, right? Our approach sort of simplifies that problem by saying, look, existing systems give you great support for partitioning and traditional replication, and we're just going to assume that they're really good at it. So we're going to bias in favor of these approaches and bias against this new approach that we're arguing that you should revisit, replication for predictability. How do we do that? We can just assume that accesses are going to be evenly distributed across partitions. So that means we're increasing the performance that we would expect to see from partitioning or replication for throughput. And then we're going to be accurate on replication for predictability. So that's what this model does. And the basic intuition here is we look at a CDF distribution like this one, and from the CDF distribution, we take our latency bound. Here we're looking at a bound of about 15 milliseconds. And we look at the intersection point with the line, and that tells us the probability of an SLA violation with no concurrency, no queuing, not considering any of the dependencies that happen between network latency, and also possibly workload changes. So here's a whole big chunk of formulas. I'll motivate really just the intuition here. So the probability that an SLA violation is going to occur is going to be 1 minus the result from the CDF. We can come up with a very general formula if we don't want to assume that the CDFs are the same across the duplicates. But if we do make that assumption, this actually just boils down to good old calculus, a geometric series, right? Where the expected SLA is 1 minus, typo, raised to the n here. Gosh, it's bad when you have things highlighted that the typo. So 1 minus the probability of an SLA violation raised to the n. So that means in order to have a violation, all of our duplicates have to incur this violation independently together. Right? So we do consider two key dependencies, right? So you've got network latency and you've got queuing delay, right? Both of these things are going to make it harder to meet a latency bound for all of your duplicates because they all suffer from these measures, these effects. So we use a MG1 queuing delay model and we just use the CDF, the cumulative distribution function of your network latency. And the way the novel idea here is how do you incorporate these, right? So going back here, tau is our latency bound. So our point here is that adding in queuing theory, or adding in queuing delay and adding in network delay affects your tau for each node. So now we have a model that is a function that has this modified tau for each node, modified latency bound. And workload changes require some additional support like runtime monitoring, which we're also doing to deal with changes.
So you're just using the average value of the network delay and the average queuing delay then? Or are you actually modeling the variability as well?
Yeah. So we are using the average queuing delay, the average network latency. We could go more complex, but in a couple of slides I'm going to show you that we're pretty accurate, so we decided to keep it as simple as possible for now. There is, I think, another Sigmetrics paper here that looks more into that variability, but we're not at that point yet. So here's the key plot on the model's accuracy. So we issued nothing but writes, still not dealing with queuing delay at all. So bear with me on that. 1 million accesses, and we add a duplicate after each one of these rounds of tests. And recall, we're predicting percentages here. So absolute error, as you've typically seen it, isn't really relevant here. So we look at the absolute percentage point error between our predicted percentage and what we actually observe. And you basically see only one line here, which is great, right? It shows that our model is accurately predicting the service level as we scale up. And to make that more clear, at each point, we're plotting the prediction error, which in terms of absolute percentage points is pretty darn low.
So what is your observed here? Is that simulation or is this on actual hardware?
That's on actual hardware. So this is, we just ran Zookeeper. Zookeeper with one node apiece. So this is a very fast version of Zookeeper. But yeah, this is on our.
When you say servers used, do you mean you're now in the replication regime, or just that there's partitions?
These are just duplicates. So we're only looking at our ability to predict the behavior of replication for predictability right now, because that's where we want to be accurate.
So when you say 8 on the x-axis, you're actually sending all requests to all 8?
Exactly. Exactly. And so the other takeaway from this is not just our accuracy, but how high we can get, right? So you can start to see an idea of the level of nines that you can achieve through this approach that we've historically dismissed because it doesn't improve throughput, but it does improve predictability a lot.
So these are duplicates, meaning they don't know about each other? You're issuing 8. So it seems like if you're doing 8 totally independent writes, then the read is going to be the worst case read time, not the best case read time, because you have to wait for all 8 to come back to see which one is the most recent or something.
Yeah, he says he's not leaving.
Right.
Okay.
So see if I can.
Is there a story about that coming, or should I wait? Or
yeah. So the story about that is there's not a story about that here. Maybe we'll talk about it offline. We deal with that. You're right. Reads can be slower. We evaluate that. It's not bad. It's a function of your throughput slowing down, not a function of your latency slowing down, which is what we really care about. But we'll talk about that.
How many trials is this? Each of those points?
1 million. 1 million accesses apiece.
Those prediction errors are
They're unbelievable.
They're so
Yeah.
incredibly low.
So once again, this is percentage point error, right? So we're looking at and this is very different from latency. So you're looking at a tail where you can have a small percentage point error can correspond actually to a lot of latency, right? So even a 1% error, for instance, at the 99 percentile, actually would be awful in terms of latency, right? A 1% error would mean that you were mispredicting by almost 3x, right? The difference between the 99th percentile and the 99.9th percentile, right? So take that with a little bit of a grain of salt here. This is a metric on percentage points, not on latency. So that's a little bit different.
To restate Jay's astonishment, it seems like with real hardware, it's unlikely that you could even run the benchmark twice. Forget prediction for a second. It seems like the repeatability wouldn't even reach that level, let alone predictability. I mean, especially if you have these asynchronous background tasks like buffer flushes that are sort of happening out of your control, or DNS timeouts. The list of explanations that you gave for
so
over 1 million samples.
yeah, you're looking over a large sample space, right? Is the whole point here, right? So if I, for instance, tried to convince you, actually, yeah, my students have trouble with this all the time, right? So they often want to run these smaller experiments. Hey, look, we want to understand 99.9%, just run 3,000 experiments, right? But that only gives you 3 sample points. So now your variability is very high if you're trying to understand this 0.001 level. But you run 1 million, that variability is going to go toward a mean of some sort, right? Just using the law of big numbers, right?
You're still only getting 1,000 points, right? I mean,
Yeah.
if you're trying to figure out your 99.9 percentile, that's dictated by 1,000 out of the million requests.
Yeah, it's well,
And
5 is enough for a t-test. 1,000 is quite a bit higher than that, right? So
But I wouldn't expect prediction errors of 1 in a million out of 1,000, given an n of 1,000. Maybe I'm misunderstanding what the prediction error is. It's the prediction error of what? Of the service level?
So it's for instance, we predict 99.10%, and we observe 99.102%, something like that, right? So, well, in any case, we'll sort of move on past this. I would like to talk a little bit about queuing and yeah, maybe breeze through the actual results before taking questions. So what we're looking at here is probably the important plot for those that want to understand how do you combine these two techniques together. So on the x-axis, we're looking at utilization. So we're increasing the utilization on each duplicate up to 1, right? And on the y-axis, we're looking at the expected service level according to our model, right? So we're able to understand the performance of using just replication for predictability only using the results that I just showed you. So that's if we just have 4 duplicates. Their utilization level will all be the same, right? And you just feed that into our model. We can also understand the effect of using these traditional approaches only, right? Where we biased toward no consistency overhead, evenly distributed partitions, right? And then we compare what we're claiming, what we really want to sort of move people toward doing, or well, what we're doing in my group, and it's working pretty well, is the mixed approach, where we're doing a little bit of both depending on the workload. So first thing to note is that we really should reconsider replication for predictability in our system design. Why? Because if you want to have a very tight latency bound, here we're looking at 3.5 milliseconds, which is just a little bit longer than our mean latency, I think about 25% longer. You can achieve service levels that you just can't achieve otherwise. So if we use 4 duplicates, we can get a service level that's pretty darn high. But if we use just 1 duplicate, we're talking about orders of magnitude lower, right? I'm sorry, not just, if we used only replication for predictability. So that is if we just distributed each access to just 1 node and didn't get any of the variability gains that we get from replication for predictability. If we, the second takeaway here is, the second takeaway is the comparison between these 2 plots. So the problem with replication for predictability is when you have queuing, as queuing increases, you get this huge drop off because once queuing gets to be larger than the benefit that you're getting from cutting into this tail, you know, the performance benefit goes straight down because your node is basically fully utilized and you're not getting any performance, any gains. So if we did this at the 3.5 millisecond level, right? Even though we can achieve very high workload, very high SLAs under very light workload, as soon as the utilization gets larger, we hit a cliff. Now, that said, if you increase tau, right, up to 15 milliseconds, you can go a lot longer, right? So takeaway 2 is revisit this because for realistic latency bounds that we care about now on the order of maybe tens of milliseconds, we can still, even just using this approach, get up to a decent level of utilization.
So what's, I mean, in practice, what levels of utilization do you see?
So we're looking at 20 to 30% utilization for a key value store that needs to give you very high response times.
So like that's what you'd see like if you looked at Facebook's utilization, for example. Like if you looked at their workloads.
Well, so you know, I don't know Facebook's, but
for reasonable workload generation.
Right. The issue here is we've long known that queuing delay means low response times, right? And while there was a lot of work, maybe mid-2000s, that was looking at consolidation and how can we consolidate things to increase the utilization, but really, once you get around 50% utilization, people get skittish about the effects of queuing delay. So I think in practice, you're really looking somewhere around this range of, well, I mean, some people run as low as 10%. For instance, our CIO's data center, they just don't use, they have no utilization at all. Some more cost-efficient approaches may push you up to 55%. But, and then the most important takeaway from this is, hey, look, you don't have to deal with this curve, this drop-off at all if you take a more modest approach, right? So if you look at the utilization that you're facing and decide to use a mixture of replication for predictability and partitioning, you can get the same type of curve that you would see here with just using partitioning only, but you can just tick up the service level that you can meet by using the two in combo. All right, so big picture slide. So I won't take any more questions just so I can finish in just a couple of minutes. So big picture slide here. This is an early depiction of our implementation, right? The key idea to support writes and write order consistency is that we issue all writes through a message repeater, a multicast message repeater. Ideally, that would be in hardware. We did it in software, and we still got pretty good performance results. We took a lot of pain to implement this in a way that is agnostic to the key value store that is on the back end. So we've implemented this with Zookeeper back here and with Cassandra in different configurations of both. We do some system monitoring data, and we have a couple of, tried and true systems implementation techniques, right? Like if we put this message repeater in the loop to the data path, we've created exactly what I was telling you we're worried about, which is these things that are common to all duplicates, right? That could cause problems for all duplicates. So to minimize its effect, our implementation uses a low overhead callback. So we send writes directly back, or we send responses directly back to the client rather than going RPC style back through the repeater. General overview. Last but not least, I wanted to show you guys this stuff about GridLab-D. So this is sort of looking at the layout of agents in GridLab-D, issuing reads, doing some computation, and then finally at the end of a time step, issuing a write back to the key value store. So you can see this sort of, I don't want to call it a barrier, but you can see the issue here, right? So until these writes complete, you can't move forward to the next time step. And James, along your question, this multi-phase scientific computation, it's been well studied, the fact that these scientific workloads that run a long time go in and out of different types of phases, and ours is no different. So on an open workload, I'll just skip to the end-to-end test. So here is the takeaway plot. So we're showing performance improvement as you would typically expect it, right? So the relative performance improvement between two approaches. So using just the partitioning approach versus using the combo approach of partitioning and replication for throughput, where the combo approach is chosen by our model. At the far end here, we're looking at the total running time of a GridLab-D simulation over the course of 3 days. And we're getting about a 20% improvement when we compare same size storage systems. So using 8, 16, or 32 nodes, where we use only replication for predictability, or mixed, right? So same number of nodes. We're getting a consistent performance gain there. And we get that by reducing the 99th percentile significantly, right? So we've significantly reduced the straggler effect here. And to be sure, that this isn't just something that happens on my cluster and nowhere else, we took this, we ran it on EC2 in order to scale up to larger sizes, and as you can see, results are still consistent there. Actually, EC2 works even better because there you have a lot of variability. I mean, we were able to, at one point, literally watch our CDF change without touching anything, right? So this is end-to-end test. Conclusion, basically, if you walk away with anything, here are the 4 points. So we're looking at these emerging workloads that need low latency on thousands of accesses. This is our target. This is what we sort of see going forward into the future. what we're suggesting is that the systems community may want to revisit replication for predictability, this old approach where you send you send the same request to many nodes and take the fastest response. It actually makes sense now for these types of workloads. And Zoolander provides all this support that I had previously mentioned. And you just saw our results on end-to-end scientific computing workload. And then these are all of my students that have contributed to some of these projects that I've talked about today in one way or another. And I just wanted to, even though they are not here, in case they see these slides, I wanted to make sure they knew I was thinking about them. That's it. So time for Q&A. Ran over a little bit.
So in the simulation, I just wanted to revisit this consistency thing a little bit. How many barriers were there in the run? I mean, is it there was one global barrier that separates two phases, or were there very frequent barriers all throughout this?
So it was more like a one global barrier. So you would operate, all of your agents would do what they're going to do for one time step, then...
Sorry, I guess my question then was how many time steps are there? In other words, how many times during the execution was there a barrier? I would imagine there must be a lot of them.
Yeah, we did it at 3-second granularity over 3 days. So, but even that's not clear because you have intermediate. So if you want to do that math, how many 3-second?
Yeah. 86,400. So,
Like a boss.
Yeah. Okay. So it still seems like if there's this barrier where everybody has to write before anybody starts to read in the next time step, it still seems like there'd be this problem that if you're releasing the write barrier after the fastest write, then the readers would have to wait for the slowest read to make sure that they got the fastest writer. In other words, or conversely, you could wait for all writers to complete, and then you could wait for the fastest reader, but you can't do both.
Right. So here's the way we handle that. So if you need strong consistency, what you do is you send writes and reads through this FIFO multicast repeater that I issued to you. So what that does is it serializes everything, right? And that can get a throughput of...
From all the clients, you send it to the same?
Yeah, you send everything through this multicast repeater.
Scale the middleware. The middleware scales for hundreds of nodes per inch, hence.
Yeah, so then you'd have to use multiple, but FYI, this is standard practice for achieving this type of strong consistency, right? Zookeeper does the same thing. Zookeeper, lazy base was just a Eurosys paper this year, right? So if you want strong consistency, you have to pay a performance penalty for it, right? And that means you're...
Zookeeper is not for high throughput data, it's just for
right. So
very low throughput coordination. That's fine for Zookeepers.
Yeah, you can go with quorums, and what quorums can do is allow you to sort of mask the effect on reads while lowering your throughput on writes, right? Or you can take this approach where you just pay the penalty on both, right? And so that's sort of our trade-off, right? If you want read my own write, we can do that a little bit more efficiently. So when we respond back with the fastest completing node in the write, we can also respond back with an address, which allows you to directly issue your read back to that node again. And if that node is, for instance, a Zookeeper group that is 3x replicated, then you can scale that read performance by adding nodes. Does that make sense?
Are there background tasks on this centralized thing then that, I mean, it seems like now that you got a
on the software repeater,
there's going to be some CDF there of
yeah. That's exactly why. Well, earlier I mentioned this. We have to take approaches to implement that as well as we possibly can, right? You're right. Some things are just going to be caused by this message repeater in between.
But that's a stateless component, right?
Yeah. So it's not that hard to implement it very well, I think. But I implement systems, so. And then finally, if you want write order consistency, then the issue is then if you can deal with some inconsistency in your reads, which a lot of these other systems support, then you just get the write back from the fastest, and then you issue your reads to whomever, and eventually you're guaranteed that everybody will eventually give you the same write performance. So our raw throughput numbers are comparable to existing systems, right? So we're not making any fancy trade-offs there.
So just general applicability of this, I just don't understand. You scaled out your middle tier to maybe tens of hundreds of machines. You scaled out your storage tier to tens of hundreds of machines, and now you put in a single bottleneck between them. Just linearize all the storage access. I don't understand how.
Well,
so it can work if you're
well, that's only, but you're talking about a very specific type of workload, right? So you're really talking about, hey, if I only want sequential strong consistency, right? Then you have, this single bottleneck. That is a problem, right? But if you don't need that, we can still scale your reads, right? By doing, if you're willing to relax that. I think, I don't want to get into trouble by saying anything too bold, but when people scale out nodes to support sequential consistency, it's often either to improve read throughput or for availability. You very rarely, by very rarely, I mean I can't think of anybody off the top of my head that gets high write performance while supporting strong consistency. That's not a fair comparison there.
I agree with that.
Alrighty, we're running late, so I don't want to drag on too long. Let's thank our speaker again.
Thanks for hosting me. Thank you guys. It was a pleasure.